We're reviewing for your first exam that you'll be taking in the Zoom session on Thursday. And so I've just pulled up a Jeopardy game, and it's a class against the instructor. And so you guys just chose what you wanted, which was implicit differentiation for 500 points. And I'm just going to pull it up. You guys are going to take a minute and try to do the problem on your own. And then once you've figured it out and want to say what the answer is, let me know. And if it's correct, you get the points. If not, I get the points if I can show you correctly. If any of these problems you want to go over in detail, we can do that too. But right now, implicit differentiation, 500 points. Let's see what we got here. So find the equation of the tangent line to y at the point 1, 0, where x squared plus sine y is equal to xy squared plus 1. So I'm going to give you a little bit of time to do this problem. So you came up with an answer, and it seems like it's a consensus with the chat that the answer you got for the equation of the tangent line at the point 1, 0 was y is equal to negative 2x plus 2. And so let's see if that was correct. If so, you guys got 500 points. Y is equal to, well, it's a little bit different form, but if we distribute this, negative 2, it's a negative 2x plus 2, which is what we had said. So let me just now see if you guys want to talk about this really quickly. Okay, great job. And so let's just walk through this really quickly. So you are given that x squared plus sine y equals xy squared plus 1. So you wanted to use implicit differentiation. You're differentiating both sides. And doing that, you would have gotten this 2x plus cosine y dy dx is equal to, you need to use the product rule here. So y squared plus x2y dy dx. So whenever you took the derivative of y is a function in respect to x, you had to tack on this dy dx. So doing that, I just quickly noticed I had some terms with dy dx. I got these on the right-hand side of my equation and factored out that dy dx. And then I moved everything else onto the right-hand side, so I subtracted 2x and moved it over here. Factored out to the dy dx from both of those terms, and then divided. Once I did that, so this is our derivative, dy dx. Using implicit differentiation, I went in, and wherever I saw an x, I plugged in 1, and wherever I saw a y, I plugged in 0. And that gave us our slope of the tangent line at that point 1, 0. So we found that our slope was equal to negative 2. Then I plugged in my point 1, 0 into y equals mx plus b, and my slope negative 2, and solved for b, and I got b was positive 2. So once I know what b is, I know what my slope is, I know what my equation of the tangent line was at that point. In this case, y equals negative 2x plus 2. Got a miscellaneous for 300. And this was one that we haven't quite covered yet. So we're going to actually go back. Oops. And so let's just jump up to 400. I believe that one you have been able to do. This is a good one. So given the chart, so you're given x when it's 2, x when it's 4, and you're giving your function f of x, g of x, your derivative function of f of x, and derivative function of g of x. We want to find the derivative at x equals 2 of the following using the table. And we're trying to find the derivative of this capital F of x when it's a composition of two functions, f of g of 2 of x. So go ahead and see if you can do that one. So it comes out that you guys think the answer is negative 18. And so let's see. And the correct answer is -3 times 3 times 2, which is -18. When you take the derivative of this, you had to use your chain rule. So let me just... So on these, I really like these problems. And so first thing that you had to do was you needed to apply the chain rule. And so I tend to apply the chain rule before I go in and plug in that X value that they're asking us to evaluate. And so looking at this chain rule derivative of f of x, we had to apply the chain rule. So our outer function was the f. And so we look at the derivative of the outer of the inner piece of this inner piece, so it's the g of 2x times the derivative of the inner. But when we take the derivative of this inner, g prime of 2x, notice we have to use the chain rule again. And this is probably where, if you didn't get this right, maybe where you messed up. And so we have to take the derivative 2x. So I said I was taking it, I didn't quite take it there. And then I started to go in and plug in. So I looked at my rule that I had, and I went in, and wherever I saw an x, I replaced it where x equals 2. So if we look at 2 times x, which is 2, we get that inner piece here is g of 4. Again, if I plug in 2 for x, I have g prime of 2 times 2, so g prime of 4. If I take the derivative of 2x, though, that gives me back just 2. There's no value there to plug in anything for x. So then I looked at the table. I don't have the table right in front of me, but looking at the table, you should have seen that g of 4 was 2. You should have seen that g prime of 4 was 3 times this 2 here. We still need to evaluate f prime of 2. Looking at the table, you would have seen that that was -3. So -3 times +3 times 2, we get back -18. And so your team gets another point, or not points, but you get 400 more points. So you're at 900. Okay, so new category or same category, but which category, how many points do you want? So the next question, it was derivatives 2 for 500 points. And the question says, compute the second derivative using any method of your choice. I'm sure a lot of you are going to be using the formal definition of derivatives there, right? Of y equals sine squared of 4x plus 9. So if you're watching the video and not live, then pause the recording and do these and then see if you got them correct. Okay, so we got an answer, and the answer was 32, parentheses, cosine squared, parentheses of 4x plus 9 minus sine squared of 4x plus 9, and then end of parentheses. So let's see if that was correct. So it looks like it's correct. You just factored out the 32 instead. Okay, so you guys get some more points. And then let's just kind of walk through that together really quickly. Okay, so the example again was y equals sine squared of 4x plus 9, and it wanted us to find the second derivative. So first thing that I did was I rewrote this. The square here is the same thing as saying the sine of the function quantity squared. And so from there, we can use the power rule, so our chain rule. So we're going to bring down the 2 in front. That's our outer function. Sine of the inside, of the inside, which is sine of 4x plus 9 times the derivative of the inside. Notice when we take the derivative of the inside, we're going to have to use the chain rule again. And so looking at the derivative of the inside, the derivative of the outer function, and our outer function right now is sine, is cosine of the inner piece, 4x plus 9, times the derivative of the inner piece of that, which is 4x plus 9. So now we have this 2 here times the derivative of 4x plus 9 over here. Well, the derivative of 4x plus 9 is 4. So I just took my derivative of that, which is 4 times 2 to give me this 8. Sine of 4x plus 9 times cosine of 4x plus 9. Well, that's just the first derivative. And they wanted us to find the second derivative. So when we find the second derivative, we need to now apply the product rule. So I chose 8 times sine of 4x plus 9 as my first function and cosine of 4x plus 9 as my second function. So using the product rule, well, 8 stays alone. Derivative of sine of 4x plus 9 was the cosine of 4x plus 9 times the derivative of the inside, which is 4, of the second, which is the cosine of 4x plus 9, plus the first function, which was 8 sine of 4x plus 9 times the derivative of the second. Well, derivative of the cosine is negative sine of the inside, 4x plus 9, times the derivative of the inside, which we found was 4. So just multiplying our coefficients in here, 8 times 4, that gives us a 32. And here we have 4 times 8, and there's a negative 1 here. So that's going to be a minus 32. And cosine of 4x plus 9 times cosine of 4x plus 9 is cosine squared of 4x plus 9. And this sine x of 4 plus 9 of sine x plus 4 plus 9, we can rewrite as sine squared of 4x plus 9. So we can leave it like that, or we can factor out the 32. If that had been a plus in between, we could have used our rules of cosine squared theta plus sine squared theta is 1, but that minus is there instead of a plus. And that would have given us 32. So you're computing the derivative using any method of your choice of y equals, this is a quotient, our numerator is z, all over our denominator, which is the square root of 1 minus z. And that 1 minus z is all underneath the radical. Okay, so this is the first time that we've gotten different answers. And so looking at this, let's see what the correct answer is. And it's definitely not in the form that I put it in, but this says 1 minus z plus z all over 2, square root of 1 minus z all over 1 minus z. They should have put this in. Let's clear our complex fraction. So let's look at that. If we cleared the complex fraction there, let's actually just look at walking through this one together and see if we get the same result if I cleared the fraction. And that's exactly what I got before I cleared my complex fraction. I think I got the points for this one, guys and gals. Okay, so this is what we were looking at, y equals z over the square root of 1 minus z. First thing I did was I rewrote it without the radical, and I put z all over 1 minus z to the 1/2 power. So we need to, in this form, use the quotient rule. And so the derivative of our numerator z was 1, of our denominator, which was the square root of 1 minus z, minus the numerator z times the derivative of the denominator. So we're going to have to use the general power rule and chain rule. So we bring our power down front, 1/2 of the inside, minus 1 from our exponent gives us negative 1/2. But don't forget to take the derivative of the inside, and the derivative of 1 minus z is negative 1. And so here I have this negative and this negative. So that gives me a plus in between. And then I just rewrote it a little bit. I kept my z in the numerator over here. I have a 2 in the denominator, and I rewrote this to have a positive exponent by bringing it down to the denominator and rewriting it as a radical. So we can get rid of this complex fraction by multiplying both the top and the bottom by 2 square roots of 1 minus c. And so if you distribute, that's going to clear our complex fraction, and we'll be left with 2 times a whole quantity. Well, square root of 1 minus c times square root of 1 minus c gets rid of this radical, leaving us with just 1 minus c, plus, well, our fraction goes away, just leaving us with z there, all over our denominator. I just kept it in factored form. I guess I noticed that this is to the first power, which is the same thing as this to the 1/2 power. Same base, we could add our exponents if we wanted to. Just distribute our 2 and then combine like terms. So we have a 2 minus 2z plus a z. Well, 2z plus z gives us negative 1z, and there are 2 out front. So I want to touch on one thing that I noticed grading your group projects and your group projects. Good job, everybody. I was really impressed on some of those. But a lot of times you guys were writing down things, you technically was wrong. For instance, and you guys put this in as the answer as negative z minus 2 divided by 2, 1 minus z, all raised to the 3/2 power. So technically this is actually, and let's say that this was just the correct answer. So let's say that this was instead was 2 minus c here. This is wrong because you don't have, and you need your parentheses around the whole numerator. If you don't have those parentheses around the whole numerator, basically what this is saying is you have 2 minus and just z in the numerator over 2, 1 minus z to the 3/2. And I noticed that a lot. So if you had more than one term or grouping in the numerator, a lot of you forgot to put your parentheses or your brackets there. And so technically that is not mathematically correct. And if I saw that on a test, which you guys probably wouldn't write it in that form anyways, I would probably knock off a little bit of points there. So I just wanted to go over that. Okay, so we have graphs for 300. Find the equation of the tangent line of the following function at the point specified. So we're looking at y equals cosine of x. We want to find the equation of the tangent line of y equals cosine of x at x equals pi thirds. Pause the recording, try and see if you got the same thing. Okay, so it looks like you guys got the correct answer, but let's just push the space bar showing the correct answer. And it was actually in a different form than ours was. And let me just go over this. So this was in point slope formula, where we put ours in slope intercept form, which makes it easier to graph. Let me just go over this really quick. I'm going to change my share. And so we want to take the derivative of cosine of x. Taking the derivative of cosine of x was negative sine of x. We needed to figure out what the slope was when x was pi thirds. So plug that in for x into the derivative. So we get negative sine of pi thirds. Well, I know sine of pi thirds is the equivalent to 60 degrees. Sine of 60 degrees is root 3 over 2. So we have minus in front root 3 over 2. So we figured out what the slope was, and then we had to figure out what the point was on that graph, y equals cosine of x at x equals pi thirds. So if we look at y of pi thirds, we look at cosine of pi thirds, which is 1/2. So we have a point at pi thirds 1/2. We plug in what we know into y equals mx plus b to figure out what b is. And so y, which is 1/2, equals our slope, negative root 3 all over 2 times x, which is pi thirds plus b. We want to get b by itself. So we added this root 3 times pi all over 6. I put the pi out front. And then I just got a common denominator. So 1/2, I multiply by 3/3 to get a denominator of 6. You guys just had it where you didn't have a common denominator, but that's okay. And so I just rewrote that as a single fraction. And now we know what our equation of the tangent line is. It's y equals our slope, which was -√3 all over 2 times x plus b, which was 3 plus pi√3 all over that quantity 6. Okay, so I actually chose definition of derivatives for 500. So compute the derivative using the limit definition. So y equals 1 all over the quantity 2 minus x. So there might be one on the exam where I ask you to use the formal, and I would call it the formal definition of the derivative to find the derivative. And so this would be a great question to do that on. So pause the recording if you were not watching this live and try it. Okay, so it looks like you got it. The result you guys came up with was 1 all over 2 minus x, and that 2 minus x was quantity squared. And it says works varies because of, I guess, how it's written at the end. So you guys got it. Let's just quickly walk through it. And so we're using the formal definition, and so we need to look at the limit as h goes to 0 of f of x plus h minus f of x, that whole quantity all over h.
Did you mean to change screens?
Yeah, and I'm doing that right now. Trying to talk and do things at the same time is hard. Okay, so now you should be seeing the correct screen.
Yeah.
And so if we use our formal definition, this is our 1 over 2 minus, plugging in x plus h wherever we saw an x, minus our original function all over h. And so let's clear, this is a complex fraction. So let's clear the complex fraction by multiplying both the numerator and denominator by our LCD, which would be, in this case, each denominator of the fractions within. So 2 minus x plus h all times 2 minus x. We need to distribute that negative, so I just did this down here. So this would be 2 minus x minus h. So once we distribute, each piece falls away denominator, and we're left with just 2 minus x when we distribute to the first grouping, minus the whole quantity. So the 2 minus x piece would cancel out, and we'd have left 2 minus x minus h all over our denominator, and then distribute this negative and combine like terms. So we're bringing down the 2 minus x, distribute the negative, we got a minus 2 plus an x plus an h. Things cancel out except for the h in the numerator, and that will simplify and cancel with the h down here in the denominator. So now we're ready to go in and do our direct substitution, and all we're doing is plugging in 0 wherever we see an h in our function. And there's only one place that we see an h, and so plugging in 0 there, we get 1 over this 2 minus x, all times the quantity 2 minus x, which we can say is the same thing as 2 minus x quantity squared. So 1 all over 2x minus x quantity squared. So we're moving to graphs, 500 points. That's nice, or not. By the equation of the tangent line of the following function at the point specified. So we have y equals e of t, and that e of t is all times the quantity 1 minus cosine of t. We're given that t is equal to pi halves, and that's where we want to find the equation of the tangent line on that function y. So pause the recording and try it. Okay, so let me just put this up. So y is equal to, or sorry, y minus e to the pi halves equals 2e to the pi halves x minus pi halves. And we kind of got it in a little different form because we distributed this 2e to the pi halves to each piece. That, let's see, is that the same thing we get? Let me just go through it real quick. So here we are given that y is equal to e to the t all times that quantity 1 minus cosine of t. And we're given that we're looking at x is equal to pi halves, and I put pi fourths there. So first thing we want to do, and we want to find the equation of the tangent line at that value. So we wanted to find the derivative. Taking the derivative, notice that we need to use the product rule. So our first function we're going to treat as e to the t, and our second function we're going to treat that quantity 1 minus cosine of t. Derivative of e to the t is just e to the t, and then the times the second 1 minus cosine of t plus the first e to the t times the derivative of the second function 1 minus cosine of t. Well, derivative of 1 is 0 minus, and the derivative of cosine of t is negative sine of t. So minus a negative, this makes it positive sine of t. We can factor out the e of t from both of those pieces. If we do that, we would be left with 1 minus cosine t from that first piece and sine t for that second piece. Now evaluating this when t is pi halves, go in and plug in pi halves wherever we see a t and then evaluate it. So we get e of pi halves, 1 minus cosine of pi halves is 0, plus sine of pi halves, which is 1. So we have this 1 plus this 1 here gives us 2 e of pi halves. And that was our slope of the tangent line of that function y at pi halves. So now we had to find a point on that tangent line. So we used our original function and we plugged in pi halves wherever we saw a t. And so doing that, we get e to the pi halves all times 1 minus cosine of pi halves. Cosine of pi halves again is 0. And so 1 minus 0 is this 1 here. And we now have a point at pi halves comma e of pi halves. So knowing a point and knowing the slope, we can find the equation of the tangent line. I use y equals mx plus b. And doing that, we would get our y value is e to the pi halves equals 2 times e to the pi halves, which is our slope, times our x value pi halves. So notice here our 2's can cancel. And we want to subtract this to get b by itself. So subtracting this pi e to the pi halves from this e to the pi halves, we get b. And so now we have our b value, and we want to go in, plug that in for b, and we get y is equal to, and because it was t instead of x, let's write it like this. Y is equal to 2 e to the pi halves, which is our slope, times t plus b, and b was this. Okay, so that was a review for the exam that you guys are taking on Thursday.